obvious in the case V is infinite dimensional. And here's his example for why it's not obvious. So why it's not quite obvious in the infinite dimensional case, he says, if you look at L2, which is square summable sequences, then if you look at one with zeros, and then 0, right, and so forth, this is a linearly independent set, all right? It's a linearly independent set. However, it is not a vector space basis for L2 because, why? The sequence 1, what's he do here? He's got 1, 1/2, 1/3, 1/n is that's in L2? What's the, I'm sorry, what's the, oh, it's because I'm sorry, I forgot about the squaring, and it looked like the harmonic series to me. But we square them and square root. So the square root of the sums n equals 1 to infinity of 1/n squared, right? Oh, you say that that's zeta of 2? Square root of zeta of 2. Oh, square root of zeta of 2, yeah. Huh. Anyway, anyway, the point is that that's a finite sequence, that there's no possible way that we can construct as a finite linear combination of the like E1, E2, E3, dot basis. Well, linearly independent set. So like what would a basis look like for L2? How would you construct this? Maybe that's a question I can't actually answer, but like we maybe have to give up on the construction. But here's the argument. So he says this proof is non-constructive in the sense that we don't exhibit a basis explicitly, we rather deduce its existence from Zorn's lemma. So here's the proof. Let's run through it here. Let S be the family of linearly independent subsets of V. We're assuming V is the vector space, okay. All right. He says, with the usual ordering of inclusion, this becomes a partially ordered set. All right, great. And then what he does is construct a totally ordered subset of S here. And so what that's going to be is, excuse me, he's got to do it for arbitrary one, doesn't he? Let T be a totally ordered subset. He doesn't say which one, right? He just says, let it be a totally ordered subset. All right. And then he defines B, big B, equal to the union of T such that T is an element. Oh, curses. I've become a victim of my own failure to comply with his notation. This is supposed to be a scripty T. Curses, I can't. I'll get it eventually. Scripty T. There. So B is the union of all totally ordered It is the union of all sets in this totally ordered subset, right? Yeah. He says we claim that B is a linearly independent subset of V. All right. So how do you show it's linearly independent? Yeah, exactly. Let V1, V2, Vm, B and B, and alpha 1, alpha 2, alpha m in the field. And what do? He says, let them satisfy star. Right? In other words, the linear combination being 0. All right, now he's up to some kind of funny business here. For 1 less than or equal to j less than, oh, curses. For 1 less than or equal to j less than or equal to m, choose tj in, my eyes keep losing track of where I am, guys, I'm sorry, in script t, so that what? Yeah, Vj is in. Can we do that? He says, since the TJs are totally ordered, and since there are only finitely many of the TJs, all right, one of the TJs includes all the others. All right, let's call that one TL. So and he says, and then then the VJs all belong to T sub L. All right. And since TL is a linearly independent set, the star relation implies that all of the alphas are 0, which then proves that B is a linearly independent set. So it's a little bit sneaky what's going on here, right? I mean, he's using the vectors to pick out the sets. And the reason that he can pick out sets is what? It's that total ordering, right? B is the union of a bunch of T's. There must be some T. Okay. Must be belonging to some T. But the fact that the script T is totally ordered, which that means what? That means that we could compare different subsets in it by inclusion, right? I think that's necessary in order to make the steps we made here. But anyway, once you've done that, what do we got? We've got B is a linearly independent subset of V, and what have we done? Then what? What's next here? He says now B is an element of S, right? And it's evidently an upper bound. For what? I should, yeah, he says upper bound. Did you define upper bound before? We said, I guess we did. Oh yeah, upper bound. For what? Yes, script T. So that means, what do we got? Oh, we've just taken an arbitrary totally ordered set, and we have showed that an arbitrary totally ordered set inside this family of linearly independent sets is what? It has an upper bound. We have thus met the conditions for Zorn's lemma. So that what? And what's that mean? So there's a linearly independent set that contains every linearly independent set. I suppose that's what it means, huh? Right. Okay, so he says, he's actually got a little bit more here. He says he claims that maximal element's a basis for V. First of all, A is linearly independent, right? And so we just need to show spanning. He says if V is in A, then of course V is in the span of A. I mean, that's the... So what if V is not in A? He says since A is a maximal linearly independent set, A union the singleton V is linearly dependent by maximality, which then implies what? That there's alpha 1, that means that there's alpha 1 V1 plus alpha 2 V2 plus alpha m Vm plus, say, CV equal to 0, with not all of these being 0, right, such that we get 0, which means then that we can show that well, what's his notation? Oh, he chooses notation that he's just basically he says that I don't know, something like alpha j vj plus da 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 alpha m vm equal to 0. He says that there has to exist these, there have to exist vectors in A union V such that this holds because it's linearly dependent. Furthermore, it must be that one of those vectors is the vector V, because if it's not the vector V, then you're looking at a linear combination of vectors from a linearly independent set, which means it's automatically a trivial combination. So the linearly dependent combination must include the new vector V. In other words, V is equal to some of these, one of these, let's say Vj without loss of generality. All right? And so you can solve for Vj by dividing by the coefficient there. Anyway, we're using this thing we learned in linear algebra, that if we have a linearly dependent set, then we can solve for one of the vectors in terms of the other ones. Or really, we're discovering that the plus minus theorem that I stated for finite dimensional vector spaces, it still makes sense for infinite dimensional vector spaces. Like, if you take a linearly independent set and then you throw in something that's in the span of that set, then that new set becomes linearly dependent. And if it's not in the span, then it's linearly independent. I think that's still true. Anyway, there you go. We have constructed a basis, A, for a vector space, even if it's infinite dimensional. We just had to slog through some stuff about Zorn's lemma to do it. Which is why, my theme for today, I don't cover this in linear algebra. Right? Because at no point in linear algebra should I probably be talking about Zorn's lemma. Although, maybe if we had a slightly different audience, I might. I don't know. What's that? I honestly think Skimbortis is more likely to talk about Zorn's lemma in linear than I am. Well, whatever happens, happens. But the next section on infinite product spaces, I'm just going to read because I think next time we talk about topology, we should talk about quotient spaces. But basically what's done in this section is he talks about the product versus the box topology. And so the product topology is the one we talked about, which is, as he says here, it's the smallest topology which makes the projections continuous. In contrast, the box topology is just defined by saying that it's like infinite products of open sets are open. And that actually that makes more things open in the infinite context than the product topologies. Like the product topology is coarser than the box topology. In the finite case, in the case of a finite Cartesian product, they're the same thing. So there's really no distinction. But in the infinite case, the product topology given to the product of Hausdorff spaces is once more, I'm saying it wrong. The Cartesian product of compact spaces is compact when endowed with the product topology. This is Tikhonov's theorem. On the other hand, if you gave the product of topological spaces the box topology, even if you had compact spaces being taking the product of compact spaces with respect to the box topology, you wouldn't necessarily have a compact product. So that's why the product topology is preferred in that sense. We get Tikhonov's theorem. And that's proved in this section. He also proves that a function on a product space is continuous if each component function is continuous, which is kind of an amusing infinite dimensional extension of what I was talking about earlier, or what I've talked about in advanced calculus, if you had it with me, in terms of breaking continuity into component function continuity. Turns out to still be true in the infinite case with respect to the box topology. And then he also has this Alexander subbase theorem. And you started talking about subbases the other day. The basis is not complicated. It's just a set of, a basis for a topology is some collection of sets that the union of them is open. I don't think there's any condition on intersections for the basis. It's the subbasis that's got the weird finite intersections thing. So, and then there's Tikhonov's theorem. Any product of compact spaces is compact. Again, with respect to the product topologies. That's what's in section 12. Page 102 is some deep stuff. It's the same kind of arguments that I've been going through here to prove that, to at least give you at least a sketch of the proof of why every vector space has a basis. I personally don't find these arguments very easy, and I'm not, you have to have a, you have to have a love of set theory, right, to really, really get into this stuff. But anyway, next section is quotient spaces, which I think is another place where we start to build new examples which are interesting, and I think you guys will enjoy that when we get to it. And then, of course, I think